So my name is Kevin DuPriest, and I'm the CEO of Planetoid Mines. And we have been looking for about 6 years doing a deep dive analysis into a process called in situ resource utilization, and where we are able to mine resources in place and utilize them and to build whatever we need to. And so about 2 years ago, I entered a competition with NASA called Break the Ice Challenge. And we're about 140 people, and that was entered, and that down to about 41. And they've just narrowed it down to 13, well, 15 people, but 13 are eligible. I just look at the 13 and as a challenge. And then, and so we have 6 months to build a full-scale lunar excavating vehicle about the size of a golf cart. And it will go and excavate 12,000 kilograms of lunar regolith and transport it 500 meters back and forth. And we'll do that 15 days. And if anyone stops during that 15 days, if your equipment fails or whatever, that's it, you're out of the competition. And it's over. So it's all about reliability and durability.
Yeah, that sounds great. And I'm wondering, what are the milestones that you've achieved so far?
Well, like I said, initially we had patented our in situ resource utilization technology. I've kept it as under a trade secret. I'm not releasing any of that information. And then of the 4 out of the 15 we're using for this competition, we've submitted in our systems architecture, and that's completed. And that was a huge step for us to complete that, and submitted that to the Break the Ice Challenge, and that is what we are building and setting out to build right now.
Right. So just so I can like better understand, you are submitting like a proposal that has like the mechanical design of the system that you're going to eventually build, but you haven't built like a real physical unit yet. You're just trying to get to this like initial stage of being able to produce it.
So out of the 15 components that we've had, there's about 12 of them that we have built field models for, and then tested that. So they're TRL 4 level right now, and at a tipping point. And so now is the first time, though, that we are building all of them together in one: a mobility system, an excavation system, and a mining cart system. And so all 3 of those will work together, as long with a regolith conveyance system as well. And so those 4 systems will actually be built and working as a demonstration model to NASA that off-world mining is possible.
Oh, that's awesome. Dang. So I can imagine that like some of the parts for a system like that have to be pretty expensive. Right. That's why I assumed that it was just sort of in a proposal state, because, you know, like satellite solar panels cost an absolute fortune. And I imagine you need something of that sort of magnitude to power your mining robot. How are you getting around those like cost limitations?
So they did it differently in this phase 2, where all the winners receive a portion of their funding of a prize money, and that was divided. So among the 13 participants this round, we were given $38,000. So that pretty much covers the titanium wheels and the boron carbide plates that we have for it. We have a tungsten carbide ripper teeth. We've got a 2,500 pound torque rotor that will turn the bucket drums. All of those costs there have added up quite significantly. And yet we've been able to maintain it under the $38,000, which is, I think, one of the keys that we were looking at. We don't have to build space qualified system. We have to build a system to test here on Earth to ensure that it works. So we don't really need exotic materials, where I would use titanium for my wheels. I'm going to use carbon steel instead, only because I need it to be durable. I don't necessarily need it to function well in a cryogenic area environment. So I'm making some adjustments for our materials that we need, which is drastically brought the cost down, but everything's has to survive. And then at the end of the 15-day trial period, we then take it into a vacuum chamber and see if it operates and performs in the vacuum chamber. So everything has to be counterbalanced and equal. So it's good that we don't have to build one-offs, we're building two-offs. So at least we have duplicates for the systems that we're able to build. And then all of our labor, we've had a lot of people that just come on board that just wanted to be a part of it and help us. So that's helped reduce our burn costs as well.
That's awesome. I think it's interesting that like you test this inside of a vacuum chamber. So like through your like experience at NASA, what sorts of things have you noticed that can go wrong when moving like a robot from space with like Earth's atmosphere into a vacuum?
Well, a number of considerations are obviously radiation hardened electronics. When you're in space, you're going to need that. We don't necessarily need it here. Our power system, we're using lithium ion batteries here on Earth to help us do that. And then we have, I'm sorry, I lost my train of thought. Something just went by here. So go ahead and continue if you would.
Yeah, I'm just asking like what sorts of problems can occur when you go from a space with Earth's atmosphere to a vacuum?
Right. So the radiation is the biggest issue. And then there's dust mitigation as well that we have to consider. And then the vacuum itself, we have a method that we're using to convey regolith, and it was a butted box that a box just butted right up against the other one and moved it. So it sealed everything in there, except under a vacuum chamber, that box collapses. So we had to either reinforce the strength of it or whatever. So I decided to move away from the box and go to a chevron pipe design. It's a belt, conveyor belt. It has little chevron cleats in it. And as it closes up and circles into the pipe, opens as a trowel, and you dump all your material in it. And then it closes into a pipe form and you can convey it. And that was the only thing that will hold up under a vacuum, because of the cleats inside the pipe itself is keeping its form. Otherwise, it would just condense and compress upon itself. And then when it opens to the trowel mode to open up, you're not going to be able to get it because of your own microgravity. Typically, it would fall here on Earth, but now we have to incorporate another mechanism, wired brush, if you will, to brush off all the material from the belt itself so that it does fall. So there's a number of considerations of the environmental, gravity, dust, radiation, all of that can cause a system that you build here on Earth to function, to fail when it goes to space.
Right. Like the physics are technically the same, but the constants that you're dealing with are changing.
Right. The cost will definitely change along with that, especially the materials.
That's cool. Yeah, this reminds me of another like rover that I was looking at where it had this interesting feature on the wheels. Like on Earth, I'm so used to seeing like fully inflated wheels that are like pretty firm and don't really change shape much when they touch the ground, except for like a big curve or something.
Yes.
But on the moon, I guess, because like rovers can sink into the soil, they make the wheels more flexible oftentimes. So that way it sort of like spreads out on the ground, like smushes a bit, and then gets more surface area and distributes the weight more. Is that something you've done with your rover?
Absolutely. One of the best analogies I've ever heard was Dr. Phil Metzger out of the University of Central Florida. He said lunar regolith is pretty much like powdered sugar. And about 20% of it is small granular sugar, but the rest of it is pretty well powdered. And so when you go to drive on it, your wheels typically are just going to sink right through. Now we've seen some nitol memory wire wheels that have been developed that mimic a round full wheel, and but with the 12,000 or 800 kilograms that we're going to be building and hauling, those wheels wouldn't work for us in our heavy duty payload. So we went with a more of a flat compressed and with hardened A2 bar steel, if you will, for our pads to help that, because you're driving over metal shards essentially, and glass, which is like obsidian shards that have from the ejecta went up, and when it came back down, it's just just detrimental to any piece of equipment. And then it's electrostatic as well. So we really want to minimize the amount of dust that we kick up. All of our excavation processes and methodologies, they're all, we excavate the lunar regolith in chunks and icy chunks. But then when we bring it in is where we break it apart and break it down into its particles and then begin to beneficiate it and separate it into individuals because of the electrostatic component of that dust. And then when two dust particles are moved together, you get what's called Reynolds dilation, which is fluffy dust. And that causes this dust just to be static, electric, and just kind of reside, if you will, resident lunar objects that just reside in the off the ground around the surface of the moon. So
interesting. So there's like this big mixture. Oh, did I just lose connection?
I think you froze. Yeah.
Yeah. So to pick it back up,
yes.
yeah. So you were talking about like the soil and what like your robot is actually excavating. And I had a question for you there. So like this soil is just like a mixture of a lot of different things. Some might be valuable, some are not. And it sounded like you used like the magnetic properties of the actual minerals in the soil to kind of like push some stuff off and out and then collect others. Is that right?
That is correct, yes. Yeah, we have a process, mineral beneficiation process, and it is called Benny and the Jets. And Benny is able, it's a 3 conveyor belt with electrostatic, electromagnetic, and ultrasonic capabilities, not for the acoustic properties, but for the vibration properties. And so as our minerals enter into our configuration, into Benny, it identifies it by its mineral properties, able to separate them and then channel that off into concentrate right there on the fly. And that is one of our what they call MVP products, because it has application here on Earth, is where we have been able to help mining companies establish this process of concentration and separation of these waste minerals. And so typically in a underground mining situation, about 65% of everything that comes out of the ground is waste. About 30% is valuable minerals. And then the other is just of a quartz. So there's, and then they bring that up off the mining ground and they set it on the surface. That causes a lot of waste and contamination, environmental cleanup and remediation that needs to be taken care of this contaminated groundwater. But Benny sits on the mine cart underground and beneficiates, and so we're able to bring up 95+% ore, and that ore is then brought up to the surface without much water used in this process, and all the waste is left behind. So that's a process that we came up with for zero gravity and microgravity to utilize in space to separate. And we found that we're disrupting the mining industry and the way that they now are currently mining. And this process allows them to do that much more cleaner and greener in the process.
Were you going to say something, Alec?
Go ahead, Tyler.
Well, I was going to say that's really cool. I think it is important to get more greener mining, as you say. But since specifically you're really familiar with the whole like lunar mining sector right now, and you can really see what's around the corner, I'm wondering, what do you think lunar mining is going to look like within the next decade?
I know that robotic missions are planned. I know within the next decade, no human mission is planned for in situ resource utilization in the mining. So they're primarily wanting to go after oxygen at this point rather than water. And oxygen is abundant within the minerals on the lunar surface. And the process to pull that oxygen out is a lot less energy intensive than it is to split water and then separate the hydrogen and oxygen. So I think within the next 10 years, we're going to see economy, which is established already, the lunar commercial propellant architecture that has been out, has already established an economy for how much NASA would be willing to pay for oxygen and water and in situ resource utilization components. And I think within that first 5 to 7 years, it's really going to be a trying period, a testing period to see what systems perform well, what methodology works the best, and how we can achieve continuous operations. And that is the ultimate goal, is to be up there for the long term and to have equipment up there that doesn't require any maintenance. So I would think that within the next 15 years, we are going to see an abundance of mining companies and mining capabilities to really help grow the economy, provide the resources that we need, and to also begin to really focus on cleaning up the debris that's around the Lagrange 4 and 5 areas that sit above the North Pole of the moon, that are sitting around in areas that just need to get cleaned up. There's a lot of particle debris that's out there, and that's in space. So I think in space mining will probably be the first thing that we go after, and then second would be on the moon and landing. But yeah, I'm excited. I think it's going to be an exciting time for about 5-10 years from now to see where everybody goes from here. So
that's cool. So you think 5 to 10 years is actually like going to be a real peak in advancements then, and we'll really start to see a lot of stuff go on.
Yeah, most of the systems exist already. I looked at it, this maybe about 5 years ago, we looked at picking up an asteroid redirect mission. And so, and we had a great plan to bring the asteroid to Lagrange 4 to sit it there, but there was no mining. What were we going to do with the asteroid once we got it there was the question. And so that's where we began to develop mining tools. People like Honeybee and Robotics are doing really well. Blue Origin is, supporting that. China has far advanced us in our mining and in our exploration capabilities. At this point, they're spending to the tune of about $7 trillion just in building infrastructure and having the ability to mine the surface and have those capabilities. So.
Yeah, it's cool. And then if it's possible to see 25 years in the future, 50 years in the future, what does that look like?
Well, hopefully launch costs have been brought down, but the cost per kilogram to launch is going to still be pretty high, I think. And so any type of resources that we can build and complete there on space is going to help spur our economy and grow spaceports and spacecraft, and we'll be able to do a lot, I think. And I see destination points happening first, destination hotels, destination areas. I know Jed McCaleb is looking at developing a couple of those components. That's his focus. So there's individuals who are really driving this forward. And yet there are some really good ideas out there that really need to be flushed out better before they reach maturity. And I think there's a number of companies here that are doing that. And in about 25 years from now, I believe that we can see at least 1 million people in space by then.
Yeah, that's really exciting. Hopefully I'll be one of those 1 million people. So so why don't you tell us a little bit about what Break the Ice Challenge is?
It is about building a full-scale prototype rover to excavate the lunar surface and the icy regolith off the moon. And so it's about reliability and durability and a system that can survive the harsh environments. And we will have to do a 15-day operational test and evaluation, a demonstration durability test, and to excavate 12,000 kilograms in 15 days and to go back and forth 500 meters and to transport it. And that is a demonstration model that we have needed for quite some time to help advance the next phases of our Artemis missions into allowing us to go in and
robotically begin to mine resources and extract them. And so we're very excited about that. It started, like I said, 2 years ago, about 140 people, and we're down to 40, and then now we're down to 13. So, we've looked at the competition to see what is out there. There's some really good ideas. I think that we're going to do well in the vacuum chamber and surviving the 15 days. I know our durability and our materials are pretty strong, and our system architecture, I think, is pretty solid too. So, it started 2 years ago with the very first one, and we had to submit a system architecture, and then now systems design was the last phase, and now we're building a full-scale prototype.
Yeah, that's awesome. So one of the things I'm really excited about is more and more entrepreneurs are excited about space startups. And I'm wondering, since you're familiar with the area, where do you think the best place to get funding is for space startups?
I would look for vertical channels with terrestrial partners. If you're developing an excavator, go look at people who use excavation. Go look at people who have excavation tools. Definitely building a prototype is the very first component that any startup should do. You need something in hand, physical model to show that you're working this, and then make sure it has a dual application to it. Make sure that it can work here on Earth, that you can sell it here on Earth, and then it also works in space. A lot of the products that are going to be used in space need to be vetted before they go up there. And so having a dual application product is probably the best way to raise funds and get the funding that you need. And then you have VC and debt equity, which I call vulture capitalist, and you've got venture capitalist and angel investors. And I've been fortunate enough that I've been blessed enough to not need any of that at this point. Our burn rate has been very low, and but we've made some really good strides, I think, for what we've done. But it's hard. It's really hard to find the funding out there that you need. You really need somebody who is in love with space and the idea of going. They have the long-term vision of everything that you want to achieve, as well as compatible. I think finding the right partner is the right key to raise the money that you need.
Yeah, it makes sense. I'm wondering, can you give us a little more details about how you get funding without going through venture capital?
No.
No.
No, because that is a tough nut to crack. Unfortunately, I mean, angel friends and family to start you off to get your prototype. But the truth is there were what they call other transactional authorities, which are funding vehicles that the government has available for us to provide us for small one-off rapid prototyping capabilities. None of that has been executed yet. So those are funds that are available for us to use, but Space Force and some other agencies have just not released the funding, have not released the proposals, have not released what they're looking for. So it's very difficult. And I know this because I spoke with one of the consortium incubators that had about 1,800 members to it, and I was able to speak to about 800 of them, and over this past 6 years. And all of them are struggling at this prototype stage. They need rapid capabilities, rapid prototyping to show and to build their one-off product, and they're struggling with it. So they need to get funding to do that, and that's usually where they go to friends and family to raise the funds they need to do that, or they do a very dummy model of it that's not using all the capabilities. But it is very difficult outside of a VC or an angel to get the funding that you need.
Well, I appreciate your honesty. That's definitely more valuable than just saying it's easy and anyone can do it. So
Yeah,
I guess, yeah. So I guess the last question we want to ask before we let you go is, what advice would you give people that sort of want to walk in your footsteps and do similar stuff to you?
Do something else. It's been I would not want to walk this path again. It's been pretty difficult. I mean, perseverance has really played a role. There's been mornings when you've just been completely defeated. When we did our first run on our beneficiation system, and it all fell apart. That was very devastating. It took maybe a week to even want to get up and start doing something again, because it really was a major setback. And so, I'm driven, and I have the desire to see it through. Not a lot of people do that, and if you do have that, then you're going to really do well. But if you don't have it and you're looking for that 9 to 5 type of experience, this isn't for what you'd want to do. It's going to take a lot of time. Networking is another key element that is critical. Surrounding yourself with smarter people than yourself. These subject matter experts that have been just invaluable to me have helped tremendously. But I would not want to endure this again. It's a pretty difficult process. I wouldn't want to put that on anyone.
Well, I appreciate your honesty. Is there any last words you want to give?
No, it's just a very exciting time, I think, for what we're doing, and I'm glad that we have this competition set aside so that we can do a rapid prototype and a demonstration model, and hopefully that will show some technologies that will benefit NASA in the future. And go Artemis. So
Awesome. Go Artemis. I agree. That's a good note to end it on. So thanks, Kevin. We'll wrap the show up there.
Okay, great. Thank you very much.